This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today after finishing this problem is standard enthalpy of dilution, standard enthalpy of neutralization, calorific value of food and fuels, thermochemical equations, heat capacities, and there are also some different types of heat capacities that we'll also try to cover if time permits. So here we have this problem which is based on that is the relationship which is already discussed in the last class. So here we have to find the energy involved for this process which is already mentioned here. So we have to convert half moles of chlorine gas to Cl minus ion which is in aqueous condition. So for this process, what is the energy involved that we have to find out. Now for this calculation, the data that will be required that is given in the question is enthalpy for dissociation of chlorine molecule 240 kilojoule per mole, then electron gain enthalpy chlorine, that is the enthalpy change for acceptance of one electron, that value is given minus 349 because electron gain enthalpy is always negative, and we have enthalpy change for the hydration of Cl from gaseous state to aqueous state, and that value is always exothermic. So there is a negative side, 3 minus 381 kilojoule per mole. So enthalpy changes for these three processes are given. The first process, dissociation of chlorine, that is the bond between two chlorine atoms will be broken. Then after electron acceptance, that is Cl from gaseous state, now it will be converted to Cl minus ion gaseous state, and final step is from Cl minus gaseous to Cl minus aqueous. But overall process is this: half chlorine gaseous to Cl minus aqueous. So this process is already given in this that is in the problem. So we will break this. How we will break this? So from this half chlorine to G, finally, that is we are getting del H dissociation. So if we consider this enthalpy change, basically we will get Cl minus gaseous. It is half chlorine. So I will write only one chlorine, and this is Cl bracket I will write G. So this is the enthalpy change for this process. That is, we are breaking the bond between two chlorine. But as there is a half coefficient, I will write only one chlorine. The next process is, it will accept one electron and it will be converted to Cl minus gaseous. And finally, Cl minus gaseous to Cl minus aqueous. For this process, it is enthalpy change is del H hydration. And this one is del H Eg, electron gain. So here we have total three processes. Suppose this is enthalpy change for the first process, this is for the second, and this is for the third. So if we want to move from this state to this state, but direct value of del H we cannot calculate, but we have enthalpy change values for all these three steps. So basically we want to move from step 1 to step 3. Suppose this is 1 state, this is 3 state, but directly you are not going 1 to 3. What you are doing, you are first moving from 1 to 2, then basically if I'm right, okay, she's confusing, let me write it once again, and I will write it in terms of A, B, C and D. So suppose this is state A, we want to move from state B, but first we are moving from A to C state, then C to D state, and finally D to B state. Okay, so here if we want to get the value of enthalpy change for this process, so del H, which is for the process A to B, that is actually equal to del H dissociation, which is basically we are moving from A to C, then del H electron, that is enthalpy change for this electron gain, that changes state C to D, and del H hydration, which is state D to B. So now we will put all these values, and these values are already given in the question. So del H dissociation, it is 240. Then we have minus 349, and then we have this one 381. So finally we will get, okay, here the calculation is already there. So see how we will put these values. This value is 240. That is the first value. But don't forget this half coefficient, because this is kilojoule per mole of chlorine. But you just need it for half mole. So that is why you have to multiply it with coefficient half. Then this one is minus 350 and this one is minus 380. And ultimately we are getting 610 kilojoule per mole. Okay, so this will be the final answer. So this is the enthalpy change for this process when we are moving from state A to B. Here we have to know standard enthalpy of dilution. Now standard enthalpy for different types of process we have discussed. Now we will discuss it for this process, which is standard enthalpy of dilution. Now what is standard enthalpy for solution, that we have already seen, but this is there is some similarity, but it is not exactly same to standard enthalpy of solution. There is some difference. Fine. So see what is the definition. It is the enthalpy change involved for the process when a solution containing 1 mole solute. So solute must be 1 mole, and solution it may have different types of dilution. So a solution containing 1 mole solute is diluted from higher concentration to lower concentration to standard condition. Now this initial concentration which is higher and the final concentration which is lower, that may vary, but important point is 1 mole of solute must be there. And another thing is you are adding more solvent, so that from initial state, that is from higher concentration, now it is becoming lower concentration. Okay, and for this process the enthalpy change at standard condition, that is standard enthalpy of dilution. We will try to understand this with an example. So here we have taken this example, enthalpy change for dissolving 1 mole of gaseous HCl first in 25 moles of water and then 40 moles of water. So these are two different processes, right? So you have taken 1 mole gaseous HCl, 1 mole. You are adding 25 moles of water. So it is written in this way, where aqueous AQ dot means you are adding 24 moles of water. After dilution, you are getting whatever you are getting. Obviously, you are getting some dilute solution, but we have written here in this format HCl dot 25 aqueous. For this process, daily change, the value is given. So this is suppose equation number 1, and the second equation, which is completely different process. Now also you have started from 1 mole gaseous HCl, but instead of adding 25 moles of water, now you are adding 40 moles of water. So in this equation it is written 40 AQ dot, and in the same format it is written that is HCl. Now it is a dilute solution obviously, but not like before, because in the previous case also you have diluted. This is also dilution, but try to understand the difference between these two types of dilution. In the first case you have added 25 moles of water, but now you have added 40 moles of water. And the enthalpy change value, though it is very close, but still there is some difference. Okay, so this is these are the LH values for these two processes. Okay, now if we subtract the first equation from the second equation, what will happen? This term will be cancelled. This term is common in both the equations, so these two will be cancelled, and 40 AQ dot minus 25 AQ dot, it is basically 15 moles of water. And in the right hand side you are subtracting this one from this, so it will be HCl 25 AQ dot, as if you have done the dilution by adding 25 moles of water. But final equation is like this. And we know as H is state function, we can, whenever we add any equation or we subtract an equation, accordingly you can also do the same for the daily values for this individual two equation. And as you have subtracted, suppose it is equation number 1, this is equation number 2, and we have done we have subtracted equation 1 from 2. That means when you want to know the deluge value for this third process, it will be minus 72.79 minus this value. Now minus minus cancelled. So ultimately the difference is minus 0.76 kilojoule per mole. Now what is the significance of this value? Why we are doing all this? It is because this value is the enthalpy of dilution, which is denoted in this way: del H subscript DIL, and not sign means standard state. Fine. So this value will be the enthalpy of dilution, because you have started already from a solution of HCl. It is not HCl in bracket gaseous. We have not taken that. It is already some dilute solution of HCl, and further you have added some more water and you are getting another dilute solution. So basically from one dilute solution you are getting another dilute solution. But what is the difference? Before adding of this 15 moles water, there is already, it is at higher concentration, but after addition of this 15 moles of water, now it is at lower concentration. So this is basically the dilution. You have already taken some solution and now you are adding more solvent, you are getting another dilute solution, and here we have lower concentration, here we have higher concentration. So this process is actually standard enthalpy of dilution, which is not same as standard enthalpy of solution. Standard enthalpy of dilution of a solution is dependent on the original concentration of the solution. It means, just take this third equation. For this equation, whatever value you have obtained, it is basically dependent on from what concentration you have started. You have started from HCl.25 AQ, but it may be different also. So if it is suppose HCl.30 AQ, suppose I am saying, then obviously this value will change. Though it is not very drastic change, but still there will be some change. So that is why it is written here. Enthalpy of dilution of a solution, it depends from which concentration, from which original concentration you have started the dilution process, and also the amount of solvent added. So in the last statement, read it carefully. It means in this equation, whatever value we have obtained, it is dependent on the initial dilution concentration, because instead of 25 it may be 30, it may be 31, anything, okay, and also the amount of solvent you are adding. In this case it is 15 moles of water, but it may be different also. So depending on this these two factors, it is dependent: original concentration and the amount of solvent you have added. Okay. Another type of standard enthalpy we have to know, which is standard enthalpy of neutralization. Now as I am saying neutralization, obviously we have to consider some neutralization process. Now neutralization process means we have to add acid and base together, but not just any arbitrary quantity. There must be some specific quantity. So it is a change in enthalpy and solutions of an acid and an alkali react together under standard condition to produce salt and 1 mole of water. We know when we add acid and base, the product we get salt and water. Fine. Now here it is written that measured per mole of water formed. So suppose in this case you can see it is 1 mole water formed. So for the formation of 1 mole of water, the corresponding enthalpy change values under standard condition, that is actually standard enthalpy of neutralization. It is not that you have started from 1 mole of acid or 1 mole of base, whatever amount you have started. But the definition of standard enthalpy of neutralization, That is based on how much, that is how many moles of water you have obtained. So that is why the definition is based on under standard condition. To produce salt, amount not mentioned, but to produce 1 mole of water, obviously salt will be produced, but definition of this neutralization, standard and neutralization, that is based on how many moles of water formed. So if it is 1 mole of water formed for this neutralization reaction under standard condition, then you can say the corresponding enthalpy change value is standard enthalpy of neutralization. Okay, that's the definition. Here we will take one example. So we have taken hydrochloric acid 1 mole and NaOH 1 mole, both are in aqueous state, and the corresponding products sodium chloride, Na and Cl together, it will produce sodium chloride. H plus HO minus together will produce water. Now here 1 mole of water is produced. What is the change in enthalpy under standard condition? It is given in two different units, minus 57.9 kilojoule per mole, or it is 13.7 calorie per mole. Now these two values, you it is better if you can remember, because for any strong acid and any strong base, this value is always common. So what I'm trying to say, suppose instead of taking HCl and NaOH, suppose you have taken some other strong base or other strong acid, then also for the production of 1 mole of water, you will get the same value of del H. Again, you will get 13.7 or minus 57.9. So there will be a negative sign. It is always negative. Basically, it is exothermic process, always heat liberated, and it is a special case of enthalpy of reaction, because enthalpy of reaction, this term is more general term. Now what type of reaction you are doing, whether you are doing reaction between acid or base, or you are doing reaction combustion reaction, suppose you have taken some hydrocarbon, you are reacting it with oxygen, so then it is another type of reaction. So depending on type of reaction, you can change the term enthalpy of reaction to enthalpy of neutralization or enthalpy of combustion. Okay, and if it is any physical process like sublimation, fusion, then also it is fine. So depending on what type of process we are doing, physical, chemical, accordingly the name of enthalpy change will decrease. So these two values we will try to remember, because we will need it again and again. Suppose in a problem given, if the value is mentioned, it is fine, but if it is not mentioned, you just have to remember this, that neutralization between any strong acid base always show this value of enthalpy change if it is 1 mole of water produced. Fine. Now why it is showing always the same value? The reason is all strong acids, all strong bases, they are actually strong electrolyte. Strong electrolyte means they can dissociate completely into cations and anions. So when you have taken HCl, it will completely dissociate like this. All the molecules of HCl will dissociate like this. It will always remain in the form of H plus and Cl minus. It will not remain in the form of undissociated HCl. So that is why it is strong electrolyte, completely ionized in solution. Similar is also for the strong base you have taken. Here we have taken NaOH, not necessarily it has to be NaOH. And the salt you are getting NaFCl, which is also completely dissociated. And H2O we will write in this way, it is liquid. Now we will cancel, see, this equation we have not written in the form of ions. But now the same equation, this is the same equation. Now we have written in the form of dissociated ions. That is the difference between these two equations. But why we have done so? Our purpose is to neglect the common ions present both sides of the equation. And these common ions are basically called spectator ions. Because they are not actually taking part, as if they are spectator. They are present as spectator. So Na plus present in left hand side, right hand side, just cancel it. Then Cl minus, that is also present in the left and right. So what you are Now you are left with HO minus aqueous, H plus aqueous in the left hand side, and you have H2O liquid in the right hand side. So this is the net equation ultimately you are getting if you are cancelling these spectator arms. So see, as if whenever you have taken strong acid or base, you will always end up with this type of equation. So as if it is reaction between H plus and HO minus, and ultimately you are getting water. So that is the reason, as whatever type of strong acid bases you have started with, you will always end up like this. And that is the reason why for any strong acid and strong base, you are getting always this value of enthalpy. This is the reason behind it. Fine. So this is true only for strong acid bases, but don't expect it for weak acids or weak bases. Why? Because they are not strong electrolyte. Weak acid, they never dissociate completely. For example, if I take acetic acid, now all the molecules will not dissociate it like this, unlike HCl. Okay, they will not remain in this form. Some of the molecules obviously will remain in aqueous state, but not all of them. So that is why they are weak electrolyte. Okay, and as it is so, you cannot cancel the spectator ions both sides like this, because some undissociated acetic acid will always remain. So this is the reason we do not apply this value, this common value, when weak acids or bases are involved. It is only for strong acid or bases simultaneously. Fine. We solve a problem based on this neutralization. Heat of neutralization of a strong base and strong acid. See, this value is now given, which is here mentioned. Sorry, it will be kilojoule, not kilocalorie, not calorie. So in this problem it is mentioned, but try to remember these values in case it is not mentioned. The heat released when 0.6 mole hydrochloric acid is added to 0.25 moles of NaOH. So here the same reaction, the same acid base that you have just seen. But when it is 1 mole, then only enthalpy changes this value. But in our case, it is not 1 mole, right? So we will write it separately. Here we have started with 0.6 moles of HCl and NaOH 0.25 moles of NaOH. Now see, these are the amount you have added. So this is basically the limiting reagent. This is the limiting reagent, or you can say limiting reactant. Okay? So it is present in excess quantity. So as it is limiting, so 0.25 moles, it will be completely consumed. So maximum NaCl you can get, as it is 1:1. It is 1:1 relationship, right? So from 1 mole NaOH you get 1 mole NaCl only. So when it is 0.25 moles of NaOH reacting with 0.25 moles of HCl, you will be getting, that is after reaction, I am using different color here. So it will be now 0. This side it will be 0.25 moles of NaCl, and water is also, it is also 1:1 relationship, right? Moles of water. Some HCl will remain excess, which is 0.6 minus 0.25. Okay. So this is the excess amount, but we are not interested in that. We are just interested in the amount of water that is formed, which is 0.5 moles. So this is the value for 1 mole water. This is heat of neutralization for strong acid, strong base, it is 13.7 kilocalorie, but this is only for 1 mole of water. So for 1 mole it is minus 13.7. So if it is 1 mole, it is 13 minus 13.7. So when it is 0.25 moles, simply multiply 0.25 into minus 13.7. 1/4 of 0.25 means what? 1/4 of 13.7, right? So it will be around 3 point something. 13.7, 1/4 of 13.7, it is 3 point something. So see, even without doing the calculation, understand this should be the correct option, 3.425. Okay. While performing a thermodynamics experiment, a student made the following observations. What are the observations? So here we have HCl plus NaOH is of the same equation. The corresponding Delitzsch value mentioned minus 57.3. Now it is in terms of joule, but it is actually same as 13.7 kilocalorie. And there is another equation which is reaction between sodium hydroxide and acetic acid. In the right hand side we are getting sodium acetate salt and obviously water. Now both are balanced equation. In the first case Delitzsch value mentioned, in the second case also Delitzsch value mentioned. From these two information, suppose this is equation number 1, this is equation number 2. What we have to find? Enthalpy of ionization of acetic acid as calculated by the student is in kilojoule per mole. So we will try to write this equation, that is ionization of acetic acid, because that is the reaction for which you have to find Delitzsch value. So when it is ionized, you are getting this anion and H plus, right? So for this equation, suppose this is equation 3. For this, the corresponding Delitzsch value we need to know. So what we will do, we will try to arrange these two equations in such a way so that you can get equation number 3. Why we are doing so? Because equation 1 and 2, you know the Delitzsch values. So if you can somehow arrange these two equations, subtract or addition, and if you are getting equation 3, then these two Delitzsch values we can manage accordingly and we can get the Delitzsch value for this equation number 3. So how we will arrange? Basically, if you do this subtraction, equation 2 minus equation 1. So let's see what we can get if we are doing so. We will write equation 2 first. But how we will write it? See, as NaOH is strong electrolyte, I will write it as Na plus HO minus. Like this. And we have sodium acetate, CH3COO. I will write it like this because it is salt. It will remain like this in the dissociated form, and water as it is. So this is first equation number 2. And now I will write second equation, that is equation 1, but I will write it in this form: H plus Cl minus together HCl, Na plus HO minus, and sodium chloride salt, H2O liquid as it is. Now see what are the common things we have here. We are subtracting it, right? Equation 2 minus equation 1. So these two will be cancelled. This is cancelled. Then we have Cl minus both sides, that will also be cancelled. Then another Na plus, that is cancelled. Water cancelled. So what you are remaining with? So it is, yes, you are remaining with CH3COOH. Then in the left hand side you also have H plus, but remember there is a negative sign. You are basically subtracting. So final equation, if I write, in the left hand side I will write CH3COOH. In the right hand side, acetate, and also this H plus, as it is negative, I will write it in the right hand side. So basically you are getting equation 3 when you are doing this subtraction. So for equation 3, the Delitzsch value should be equation 2 minus 55.3 minus equation 1 minus, then again minus. So these two will be cancelled, plus finally it is 2 kilojoule per mole. So this should be the answer, 2 kilojoule per mole. Fine. Next topic is calorific value of food and fuels. Remember, we have already seen what is combustion. So combustion is, you have any substance, suppose you have X, you are reacting it with O2 and you are getting some product. So this is basically reaction with O2, and in this process, and which is basically combustion, mostly it is exothermic, and mostly where it is fuel, you will see it is hydrocarbon, carbon and hydrogen, though oxygen may also be present. Here you can see some fuel mentioned, hydrogen. So hydrogen can react with oxygen, it will produce water. It may be methane. So when it is methane, suppose if X is methane, you will get carbon dioxide and water, because it is hydrocarbon. Hydrocarbon, when you are considering combustion reaction, it will always produce carbon dioxide and water. Then you can have petrol, then coal, which is basically carbon, reaction between carbon and oxygen. It may be ethanol, CH3CH2OH. So these are the different compounds mentioned. But what are all these? These are basically fuels. These compounds are used as fuels. So when you are burning it with oxygen, that is combustion reaction, the corresponding amount of energy produced, that is kilojoule per gram of this compound. Suppose in general, if I say X, it is reacting with oxygen, the energy produced in unit kilojoule per gram of X, these values are given. So for hydrogen it is 143, methane it is 56. So gradually it is decreasing. For carbon monoxide it is 10. Okay, so different fuels are having different types of energy produced when it is burned in oxygen. Now why these values are important? Because just by looking at this chart, you can understand which fuel will be more efficient. So when it will produce maximum heat, obviously that will serve as better fuel, right? So hydrogen, as its value is maximum, here all the substances that you are seeing as fuel, obviously hydrogen is maximum efficient. Now this is also applicable for food, because food is also burned inside our body. So there is some analogy. But what is the definition of calorific value? Calorific value is defined as the amount of heat produced in calories, or it may be in joule, when 1 gram of the substance is completely burned, which is basically combustion process. Now this 1 gram of substance, this substance may be food, that is the reactions occurring inside our body, or it may be fuels. So fuels values that you can see, some examples are given. And for food, we can say calorific value of food indicates the total amount of energy a human body could generate during its metabolism, and it is mainly expressed kilocalorie per gram. But this is also a kind of burning process, though it is happening in vivo, not in vitro, inside our body. So we are saying it in a different way. The total amount of energy a human body could generate, but that is also kind of liberated energy, right? Fine. So food and fuels, we use this calorific value. So higher is the calorific value, obviously that will be producing more heat. More heat will be released. Higher calorific value means more heat will be produced. So here we can see some examples of food stuff: carbohydrate, fats, proteins, the three main components. Now you can compare with whatever energy they are producing per gram in Bohm calorimeter and also inside the body. In Bohm calorimeter, the specialty is here volume remains constant. Fine. So these values you can find they are almost close, though not for this one, but this 4 kilocalorie per gram you are getting for carbohydrate and protein, but for fats it is almost double amount. So when the calorific value of fuel is very high, more amount of heat energy is produced and hence it is showing more efficiency. But for foodstuff, it means that this type of food that will be when they are metabolized, more how much energy we can expect, that values you can see. So we can say that though calorific value is mostly used for fuels, but if we consider it for suppose carbohydrate and fat, if we compare, obviously in case of fat more heat liberated, so calorific value is also high. For fats, calorific value is high compared to carbohydrate and protein because it is producing more energy. When per gram there is only 1 gram of the food is metabolized. Thermochemical equations. Now see, thermochemical equations, though we are discussing it separately, but actually we have used it already so many times. Thermochemical equation is nothing but it is a kind of expression of a chemical reaction where Delitzsch values are mentioned. Fine, and that we have done several times. So, but now we will try to understand it. Though we have seen different examples already during the discussion of different types of enthalpy. Remember, standard enthalpy of dilution, atomization, enthalpy of formation, different types of enthalpy. In today's class, in last class also we have seen. But in all these cases, you have used thermochemical equation. But now we are trying to understand it separately. So this is a balanced stoichiometric chemical equation, obviously. And what is so special about it? Because it includes, when you are writing any thermochemical equation, it is always, there is mention of amount of heat evolved or absorbed. And that is denoted by Delitzsch R. That is heat of reaction. In general, heat of reaction. Now, depending on what type of reaction you are doing, there may be different types of names. But important point is Delitzsch value will always be there. In general, if I am writing there is reaction between A and B, it is producing C, and Delitzsch value is minus X kilojoule or kilocalorie per mole. Okay. So Delitzsch value is mentioned. So this is a separate branch of chemistry which is concerned with the quantities of heat evolved or absorbed during chemical reaction, and that branch of chemistry is known as thermochemistry. It is all about enthalpy. Now there are some conventions we followed. Though these conventions or rules that you will be now learning, you have already applied it. But we are just trying to discuss it separately. That is the difference. Otherwise, we have already done it. So when it is exothermic reaction, we know this value is negative. For endothermic, it is positive. Unless mentioned, Delitzsch values for the standard state of reactants or products. So suppose in any reaction Delitzsch value, whether it is standard state or not, it is not mentioned specifically, you can consider by default that it is basically the standard state value of Delitzsch. Next is coefficient of different substances represent number of moles of reactants reacted and products formed for the heat change represented in the equation. So in any equation, if there is a coefficient are mentioned. So the previous equation that I have just written, suppose it is A moles of A or B moles of B, it is producing C moles of capital C. Now these are the coefficient involved. So if for this reaction Delitzsch value is mentioned as in thermochemical equation, it is only applicable for this coefficient. But suppose you are changing this coefficient, obviously Delitzsch will also change. If the reaction is reversed, sign of Delitzsch changes. Suppose you are reversing this equation. Now the equation is C, capital C, it is producing A of capital A, B of capital B. This is reverse reaction. So for the first equation, if del H is minus X, now for this, del H will be plus X, right? That is mentioned here. If the reaction is reverse, sign of del H, that will also change. Another important point is you have to mention the physical state. Don't forget to mention the physical state, whether it is liquid, solid, or aqueous. So here this capital A, B, which are basically reactants, what are their physical state that you have to mention. Suppose it is solid, you are writing S. Suppose it is gaseous, you are writing G. Suppose it is liquid, you are writing L. So why we are mentioning this physical state, why it is required? Because depending on their physical state, enthalpy value will be changed. So this del H value, which I have written minus X, this is only applicable for this physical state. Changing the physical state, this will also change. So that is the reason you should mention that ideal way of writing thermochemical equations. So physical state of all the species are specified since enthalpy depends on physical state. Then one more point, if the thermochemical equations multiplied throughout a number, the enthalpy change is also multiplied by the same number. Now this also we have done many times. Suppose this equation you are multiplying both sides by 2. So this del H, now it will be minus 2x. So you also have to do this for del H. And if you are suppose multiplying both sides by half, then this minus x, it will be changed to minus x by 2. Okay, that is the meaning of this last statement. So these are the different rules that we have to, conventions basically, that we have to follow when we are writing any thermochemical equation. New topic, which is heat capacity. What is heat capacity? When heat is supplied to a system, you are supplying Q. Obviously, now in the system, the molecules that are present, they will absorb of heat Q, and as a result, their kinetic energy will also increase. And because of this kinetic energy increase, this will raise the temperature of the system. Kinetic energy, temperature directly related. When you are increasing temperature, kinetic energy will increase, or kinetic energy increase means temperature increase. So initial temperature, if it is T1, final temperature is T2, then the difference in energy T2 minus T1, because of addition, because of this supply of Q amount of heat. Now for this process, we can write this equation that Q is proportional to this difference of temperature. How much temperature will increase, that depends on how much Q you have supplied. Or another way you can write, Q is proportional to del T. Now proportionality sign, if we remove, we are putting here a constant capital C. This C is actually heat capacity. So Q is equal to C into delta T dot delta T. That means capital C is Q divided by delta T. Right? So this C is called heat capacity. Now C is equal to amount of heat supplied, or it may be absorbed also, divided by the temperature difference. So from based on this equation, now you frame the definition of C, that is frame the definition of heat capacity with this unit. It has to be this unit because it is Q by del T. So it should be joule per Kelvin or joule per degree centigrade. Any temperature unit you can use. So C is heat capacity, which is defined as the amount of heat energy required to raise the temperature of a given quantity of matter by 1 degree centigrade or Kelvin. So C is equal to Q by del T. But suppose this del T is 1. So when del T is 1 degree centigrade or Kelvin difference, now C is equal to Q. So under this condition, when there is increase in temperature of 1 degree centigrade, it may be decrease also if it is heat that is depending on heat absorbed or liberated. But important point is total quantity of heat absorbed or liberated at the change in temperature T1, T2 minus T1. So Q by del T, but when del T is 1 degree centigrade or 1 Kelvin difference, then C equal to Q. So under that condition, you can say that it is that amount of energy. So heat capacity is that amount of energy which is required to raise the temperature of a given quantity of matter. Now see, given quantity of matter, quantity, regarding quantity, we are not saying anything. In this equation, there is nothing regarding quantity. It is only heat, C, which is proportionality constant, and del T. But what is the significance of this proportionality constant? That is this definition. It is that amount of heat energy which is required to raise the temperature 1 degree centigrade or 1 Kelvin of any given quantity of matter. Which quantity? That is not important here. When C is large, a lot of energy is needed to raise its temperature. That means, suppose you have taken two different substances, substance 1, substance 2. In both cases, you are increasing temperature 1 degree centigrade. In both cases, it is same. But suppose for the first substance, heat capacity is high, for the second substance, heat capacity is low. So when heat capacity is that is written, C is large, a lot of energy is required to raise the same temperature difference. Okay. So if you know the heat capacity of a particular substance, then you will be able to compare in which case you have to supply more energy for the same change of temperature. So this is all about heat capacity. Next, there is specific heat capacity. Now, what is the difference between specific heat capacity and normal heat capacity? That we will try to understand. Here it is mentioned given quantity, but what is the exact quantity, that is not written. But scientists needed a quantity that has no dependence on the quantity of matter. So in this case, as you have not mentioned the quantity, basically how it is dependent on quantity of matter, directly will, that is what I'm trying to say. In this case, there is some dependency on the amount of matter, but sometimes it is required this quantity of heat capacity where there is no dependence on quantity of matter. So that is why now what we will do, in this case we have not mentioned anything regarding quantity, but now we will mention it. That is the difference. So scientists needed a quantity that has no dependence on the quantity of matter under consideration for next step. Now suppose the one thermodynamics unit mass. It may be 1 kg or 1 gram. T is same, that is basically del T, not T. It is again 1 Kelvin or 1 degree centigrade. And now capital C is Q. But in this case, when mass is fixed like this, in this case, the heat capacity that you will be using, it is now having a new name, which is specific heat capacity. And now it is denoted by small c. This is capital C, this is small c, that is the difference. How the definition will change? It is the amount of heat energy required to raise the temperature of a substance per unit mass. So now when you will take two different substances and you are comparing specific heat capacity, it is not that in both cases you are raising the temperature 1 Kelvin or 1 degree centigrade, but it is also what is the mass involved, that is also fixed. So for both substances it is 1 gram mass, 1 gram mass. So there is no matter. So that is why it is specific heat capacity. Another important difference is heat capacity, that is this first that we have learned, that is extensive. It is dependent on mass, but specific heat capacity is intensive. This is very important difference between these two, right? And now the unit will change. In the previous case, the unit is joule per Kelvin simply, but now it is not only joule Kelvin, joule per Kelvin per kg. That means per unit mass. So this is the difference in unit. Here no mention of amount, but here amount is fixed. So it is always per kg or per gram. Here it is per kg. Okay. So specific heat capacity and heat capacity, don't think these two are same. These are obviously different. Fine. .3 gram of ethane undergoes combustion at 27 degrees centigrade, which is basically 300 Kelvin, in a Bohm calorimeter. Now specification, if it is specified like this, it means basically constant volume. Temperature of calorimeter system, including the water, because in calorimeter there is always amount of that is water involved, but increase in temperature of this calorimeter system including water, because sometimes it is mentioned excluding water, here it is including water. The increase in temperature is 0.5, and the reaction, that is the combustion of ethane with oxygen, that is reaction between oxygen and ethane is C2H6, that is happening at 300 Kelvin, but increase in temperature of calorimeter is 0.5 degrees centigrade. The heat evolved during this reaction, that is combustion of ethane, at constant pressure you have to find. Some more informations are also there. Heat capacity of the calorimeter system is given 20 kilojoule per Kelvin. Look at the unit, it is joule per Kelvin. So it is heat capacity, it is not specific heat capacity. R value we know, in SI it is 8.3, and we have to assume ideal gas behavior. Atomic masses of carbon, hydrogen given 12 and 1. Why it is required? Because C2H6 is involved. So if we want to know its mass, obviously these two atomic mass values you need, right? So first you have to write the combustion reaction, the balanced equation, and that is very easy to do. I have already mentioned how to do it. I will again say it here. So first simply write C2H6, O2, and whenever it is hydrocarbon, your products are always CO2 and H2. As it is C2H6, 2 carbon involved, you have to write 2 CO2. As it is 6 hydrogen present in ethane, you have to write 3 H2. What is the total amount of oxygen atoms? See, 2, 2, that means 4. Here it is 3, that means 3. So 3 plus 4, it is 7 oxygen atoms. So if you want to balance it, you have to multiply with 7 by 2 coefficient, because 2 will be cancelled. Ultimately, it is 7 oxygen atoms both sides. For 1 mole of ethane, if we want to know the molar mass, C2H6, it is basically 2 into 12 and 6 into 1, which is nothing but 30. So this is the molar mass. So when given mass is divided by molar mass, you get the total number of moles of ethane, which is 0.01. And here 0.5 degrees centigrade, that is the increase in temperature. So if we want to know what is the heat evolved, that is Q is equal to C into del T. Here C value is 20 kilojoule, which is already given in the question, and del T is basically 0.5, that is temperature difference. So that is why you don't need to convert it to Kelvin, because even if you convert it to Kelvin, you will end up with, it is not required because it is difference. So don't try to convert it to Kelvin. Fine. So it is 20 into 0.5, it is 10 kilojoule. But 10 kilojoule, it is only for 1 mole, because it is 20 kilojoule per mole. So whatever value you are getting, that is for 1 mole. But in your case, it is not 0.1 mole, it is 0.01 mole. So what you will do, you will divide it, this 10 by 0.01. So del U is actually minus 1000 per mole. Why we have 1000 kilojoule per? So why I have taken it minus? Because heat evolved in the Bohm calorimeter, that is this. So this amount of heat is involved because it is a combustion process, but that amount of energy is also absorbed also. So if we consider from absorption, basically I'm trying to say the reaction is occurring in the calorimeter. Heat, the amount of heat that is released, that is also absorbed in the calorimeter. Okay, so numerical value is 1000, but when we will consider del U value, that is the internal energy change, it is not Q, we are considering here del U value. then you have to put a negative sign. And we will use finally this equation, that is a relationship between del H and del U, because finally it is asking the heat evolved during combustion of ethane at constant pressure. So del U, that is the not enthalpy. This is basically we consider which is at constant volume. So only at relationship between del H and del U, it is normally we write del H del U plus P del V. But as it is mentioned here that it is ideal gas, so instead of writing P del V, because we cannot use P del V, now instead of writing this, you can write del Ng RT, because PV equal to nRT. So that is why P del V we can write in this form. But we just know what is the del U value. Why it is so? Because del U is associated with constant volume, and here we are considering Bohm calorimeter, which is all about constant volume. So the value that for Q that you are getting, that is for constant volume, but we need it for constant pressure. Now when it is constant pressure, now you have to consider del H. So QP, that is amount of heat absorbed or evolved, QP means under constant pressure, then it is related to H. But when it is QV, it is related to U, basically del H and del U. So you have started with QV, but you need it for QP. That is why we are using this equation. Otherwise, this should be the correct, the final value. But it is asking evolved at constant pressure, not heat evolved at constant volume. So as it is heat evolved, so that is why there is a negative sign, because finally you have to find the answer in this format, heat evolved during this combustion process. So we are using this equation. Our purpose is to convert del U to del H, that is from the value of del H. Now we are trying to reach del H, because del H is all about heat absorbed evolved at constant pressure condition, and that we have to find. So finally put all this kilojoule, it is in kilojoule. So you also have to be careful about the units of R. R is given in 8.3 joule, but you have to divide it by 1000 to convert kilojoule. T as it is 300 Kelvin, and del Ng, how it is, why we have written it like this? Because if you use the equation, it is basically total number of gaseous moles in the right hand side is only 2, because this is liquid. So in the product, sorry, right hand side means product side. So product side you have 2 moles of gaseous substance. In the left hand side you have 1 and 7 by 2. That means 1 plus 7 by 2. Now 1 by 7 by 2, it is basically 9. So 2 minus 9 by 2, if you do calculate, you will see it is 4 minus 9 by 2, that means minus 5 by 2. And minus 5 by 2 means minus 2.5. So this is the value of del Ng. So put the value of del Ng minus 2.5, R value 8.3 divided by 1000 to convert it to kilojoule, and T 300. Finally, we are getting del H value, which is close to this, but it is not exactly same. Okay, so this should be the final answer. If you take nearest integer, it should be 1006. Okay, so we'll end the session here. Thank you for listening.